BioAFM, Heiko.
Hi, my name is Heiko. Thanks for the introduction. Can you guys see my screen?
Yeah, all good. Perfect.
Okay, perfect. So I'll be talking about how Bruker is engaged in the CEAT project. That was really nicely introduced by Louis, so that's great. But before I do that, I will start to introduce Bruker and show you some trends in BioAFM, which is the atomic force microscopy unit I'm working in Berlin, Germany. And as he said, maybe we have some time for questions later. So Bruker is approximately 60 years old, and it's sort of got a lot of innovations in their portfolio. And we're talking about X-ray, and we're talking about mass spectrometry, super S microscopy, and I'm working in this atomic force microscopy unit on the biological side in Berlin. So from the AFM side, we offer sort of many AFMs also for semiconductors and sort of physical and polymer side, but I'm working more on the biological side, so we sort of integrate the AFM into sort of different techniques like super S optical microscopy or simple fluorescence or confocal microscopes, you can see here. Or we have a recent trend I will talk about for a few minutes, is the high-speed AFM in order to get data quicker. So a few of those applications you can see here, so we can target a live cell and scan the surface of the cell fairly quickly. We can do the cytoskeleton reorganization in a live cell, but we can also then sort of extract things like the membrane and lipid phase transitions at high speeds, or we can follow sort of collagen dynamics, which I will show you also in a minute, or we can do DNA protein binding. So this is my next example. So we have a sort of a DNA origami, which we design a certain way. This is 70 nanometers by 100 nanometers. And then we put certain proteins on top of it. So this is stramidine, biotin binding. So we have the biotin on the DNA. So we integrate that into DNA origami, and we then can sort of bind this stramidine on top of it. And this is a dynamic process, so we want to understand how can we tune the binding of these proteins onto the DNA origamis. The reason we do that is if you give these proteins to a cell, you can change the way it's absorbed onto surfaces. So we found that it's quite critical how many you give per square nanometer or square 100 nanometers. You can change the binding behavior of the cell. Another example is the collagen. So we look at the type 1 fibrogenesis. So we can look in real time how this protein fiber is formed. So this is just a schematic here. You have polypeptide chain, and then with a fairly complicated process, it turns out being sort of a macroscopic fiber. We can look in real time how this is formed. What you can see immediately is 67 nanometer binding effect. If you look carefully, you can also see there's more resolution you can see across the fiber. So we're trying to investigate all these properties. But with the CEAT project, we're obviously more on the biomechanics of more sort of 2D, 3D cell structures. So most of the time we dealt with spheroids, and Louis gave you a good introduction. I come to some results in a minute, but I want to give you a quick overall idea on the project. So we thought it's a very positive project. So a lot of people in my team are engaged in it, and we did software and hardware and experimental contributions. So that was really nice for us. We thought everybody is very engaged, in particular on the academic side. We got very positive contributions and outcome out of it. I'll show you some in a minute. And generally, the project was really well managed and well organized. So that was definitely very good for us. So I want to also highlight the benefits. So what we got out of it was simply that we could understand a bit more what does the real life researcher needs and what kind of tools do we need to develop, hardware and software, to make this move forward. And we also worked out how to streamline sort of the workflow, because sometimes in the development lab, things were completely different to the sort of customer lab, academic lab, or sort of pharmaceutical lab. So that was really useful for us. And we got really good feedback also very quickly. So that's a big aspect for Bruker to join these projects, that we can get feedback. And of course, also there's more relevant biological samples for us to study, or to study together with the university in Swansea to get these results and to optimize our products. But also Bruker offers to measure something quickly for the academic side as well. So new features can be started, can be tried early, new software versions can be tried early. So it's kind of win-win for both of them. So it's really helped us a lot. So one example we had is, we used to sort of static elastic modulus calculations of cells, which is, let's say, a 2D cell layer. But what we realized also in this project is that, the static way of doing it by a simple indentation is not enough. So what we did is we realized that it's actually very frequency dependent. So we modulate now this indentation and found some interesting results. What happens at 1 kilohertz modulation on the cell. So we could actually study loss moduli and storage moduli of cells and spheroids. So that was a very nice outcome. We published that on our website. That was really well received by our customers, and obviously we worked together, so we kind of put a website together with the Swansea and the CEAT project. So that was a good outcome. Obviously, we had some challenges. It wasn't quite mentioned so far, apart from the COVID case, but that sort of held us back a bit. And we also found sometimes the synchronizing challenging. But I think we have regular meetings, and we could come by fairly efficiently now. Sometimes this is probably a problem the universities will face in these projects, that in the business side, these priorities shift quite quickly. So sometimes there's a really urgent project with high priority, and then it's going to take a while until you make more progress, and then you make a bit less progress on one side and a bit more progress on different times of the year. So that's probably a general academic private partnership issue. We just have to keep focusing and have to keep regular meetings so that to tackle that project and that problem. And we also realized that we worked on loans for a bit, not necessarily on the CEAT project, but these loan-based equipments were a bit of a hurdle. So we actually now work on permanent installations of systems, so we can get feedback quickly and provide new updates and say new developments fairly efficiently. So for the future, we want to definitely test more hardware and software together with with Swansea within the CEAT project. So that's definitely what we want to do, and also study sort of more drugs if we are allowed to, and maybe study some of these tissues or steroids that are sort of challenging or drug resistant, as Louis also mentioned in the introduction. So that's something we are very interested in. And as I said, we work on, and it worked out quite well actually, that we have now a permanent installation of one of our systems, so we can work now fairly efficiently between Bruker and the CEAT project. And I think that's it. I want to thank my team for all the work, and Louis and the CEAT project for all of their work and their support. So if you have any questions, I'm happy to answer.